This is explained binding energy curve. If a certain number of neutrons and protons are brought together to form a nucleus of a certain charge and mass, an energy EB will be released. In this process, the energy EB is called binding energy of the nucleus. If we separate a nucleus into its nucleons, we would have to supply a total energy equal to EB to those particles. Although we cannot tear apart a nucleus in this way, the nuclear binding energy is still a convenient measure of how well a nucleus is held together. A more useful measure of the binding energy between the constituents of the nucleus is the binding energy per nucleon, EBN, which is the ratio of binding energy EB of a nucleus to the number of the nucleons A in the nucleus. EBN is equal to EB by A. We can think of binding energy per nucleon as the average energy per nucleon needed to separate a nucleus into its individual nucleons. Figure shows binding energy per nucleon versus mass number. The following main features of the plot are: first one, the binding energy per nucleon ABN is practically constant, that is practically independent of the atomic number for nuclei of middle mass number 30 less than A less than 170. The curve has a maximum of about 8.75 MeV for A is equal to 56 and a value of 7.6 MeV for A is equal to 238. Second point, EBN is lower for both light nuclei A less than 10 and heavy nuclei A greater than 170. There are two conclusions from this observation, these two observations. First one, the force is attractive and sufficiently strong to produce a binding energy of a few MeV per nucleon. Second one, the constancy of binding energy in the range 30 less than A less than 170 is a consequence of the fact that the nuclear force is short range. Consider a particular nucleon inside a sufficiently large nucleus. It will be under the influence of only some of its neighbors which come within the range of nuclear force. If any other nucleon is at a distance more than the range of the nuclear force from the particular nucleon, it will have no influence on the binding energy of the nucleon under consideration. If a nucleon can have a maximum of p neighbors within the range of nuclear force, its binding energy would be proportional to p. Let the binding energy of the nucleus be pk, where k is a constant having the dimensions of energy. If we increase A by adding nucleons, they will not change the binding energy of a nucleon inside. Since most of the nucleons in a large nucleus reside in it and not on the surface, the change in binding energy per nucleon would be small. The binding energy per nucleon is constant and is approximately equal to pk. The property that a given nucleon influences only nucleons close to it, it is also referred to as saturation property of the nuclear force. A very heavy nucleus, say A is equal to 240, has lower binding energy per nucleon compared to that of a nucleus with A is equal to 120. Thus, if a nucleus A is equal to 240 breaks into A equal to 120 nuclei, nucleons get more tightly bound. This implies energy would be released in the process. It has very important applications for energy production through fission. Consider two very light nuclei A less than 10. joining to form a heavier nucleus. The binding energy per nucleon of the fused heavier nucleus is more than the binding energy per nucleon of the lighter nuclei. This means that final system is more tightly bound than initial system. Again, energy would be released in such a process of fusion. This is the energy source of the sun.